Just as MATLAB has a function, autocor, to find the autocorrelation coefficient, there is also a function, parcor, to find the partial autocorrelation coefficient. To show you this function, I will first create a transfer function, which is no longer a moving average, but rather an autoregressive model. Rather than creating it with TF, I will create it using ZPK, specifying the zeros, the poles, and the gain. I will do this because in this case, I have to worry about where the poles are. I do not want an unstable transfer function. So, no zeros, this is the gain, and I will put here some stable poles. This here is the output. And finally, I will calculate the partial autocorrelation for 25 legs, that is to say, for a period of time up to 25 times the sample time. Remember that I need not specify here a number of legs. A reasonable value is found if no number of legs is specified. Those limits, calculated as 2 divided by the square root of the number of samples, are shown as well. Also remember that these limits are slightly off. 2 is rounded from 1.96, or better still, 1.9599, etc., etc. So we will rather commit the error of allowing more parameters than necessary, rather than too few. Let us run this section and see what happens. Here is the transfer function. We have 1, 2, 3, 4, 5, 6 parameters. 1, 2, 3, 4, 5, 6 values of the partial autocorrelation function clearly outside these bonds here. So you see, we use the partial autocorrelation coefficient for an autoregressive model, just as we use the autocorrelation coefficient for a moving average model. We use these correlation coefficients to find a reasonable size for a model with which I should try to identify the plant with this output when the input is random. Also notice that in this case, the input is random, but not an approximation of white noise, since it has a mean value different from 0. There is no problem because I am using the correlation coefficient. This partial autocorrelation coefficient does away with the mean value, just like the autocorrelation coefficient does. In this way, as long as the input is random, I can find a fairly good estimate of how many parameters I need. Also notice that, of course, there are numerical mistakes. I may be overestimating a little bit the necessary number of parameters. I may be underestimating it a little bit. So in real life, with this result, I would probably type 1, 2, 3, 4, 5, 6, but also 7, also 5 parameters for an autoregressive model for the plant that has this output. And then, of course, compare the results using the Akaike information criterion and the Bayesian information criterion.